Greetings, everyone. Today we'll continue our lesson, and actually we get to do limit laws. So basically today we are learning on how to evaluate limits without having to, because on the last class, each and every time to evaluate a limit, we had to use a table. We learned the definition of a limit and when do we say the limit exists, and the vertical asymptote that we did. But today, actually, we are learning on how to use these limit laws. And most importantly, we're learning on how to evaluate limits without having to draw up a table or without having to use a calculator. And lastly, we get to learn about squeeze theorem. Squeeze theorem is a very important theorem in mathematics. So, and that is what we'll be doing today. We'll start first with the limit laws, explain what laws do we use to evaluate limits. Then from there, we can continue and with other lessons, because tomorrow we'll be talking about epsilon delta definition. So basically we'll be evaluating limits without not using limit laws. But when do we say that L is a limit? What should happen? Which criteria? Because from the previous lesson, we said, as we get close, but someone may ask actually, when you say close, how close is close? So basically tomorrow we'll be generalizing that using the epsilon delta definition. And please don't take that lightly. It can be confusing for many, but otherwise it's a very important principle in mathematics, especially for those who are doing third year mathematics. So basically tomorrow's class can help you to be able to handle or to have just a bit of clue to be able to handle third year mathematics. So let's jump into today's class. As we said, today we are evaluating limits. So that's what we're going to be doing. Since you don't need to see my face, to look at my face, I'm going to stop showing myself so that we can just focus on the lesson that we should be doing for today. Maybe let's recap on what we did the last time. We spoke about the limit, and we said actually the concept of a limit is just basically just investigating how a function behaves near a certain value in the domain. And we introduced this notation, and we said this notation, we can read it as f of x is approaching L as x is approaching A. And again, we say that the limit exists, or L is the limit of f of x as x is approaching A, if and only if the limit of f of x is approaching L, if x is approaching A from the left, and very important, the limit of x approaching A from the right, f of x is approaching L. So if the f of x is approaching L, when x is approaching A from the left and from the right, that's when we say the limit exists. Please note that this part of if and only if, it's very, 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 very much important. Maybe to give an example, every truck is a vehicle, but not every vehicle is a truck. So that is one example of showing you that actually sometimes something can imply something, but the reverse is not true. So if and only if, it means that if we say that the limit exists, that means that we say that the limit from the left and the limit from the right are the same. And again, if the limit from the left and the limit from the right are the same, it means actually the limit exists. So that's why we have this if and only if. It's not an if, but it's an if and only if. So it means actually it works in both ways. It means if the limit exists, it implies what we have on the right hand side. And if we have the left hand side, it implies what we have on the right hand side. And again, we spoke about the vertical asymptote. We said if x approaching A, some certain value A, and f of x becomes bigger and bigger, then f of x, we say that it goes to infinity or it goes to negative infinity, like you can see here. Then these are the left and right sided limits. And again, we did emphasize that infinity is not a number, but the limit of f of x as x approaching a going to infinity just means that f of x is increasing without bound as x is approaching a. And same thing as the f of x going to negative infinity just means that f is decreasing without bound as x is approaching a. So let's get into today's lesson. We're going to talk about limit laws. So before we get into the laws, let C be a constant, meaning it's some real number, some number, and such that the limit of f of x is approaching a, it exists. Remember that means it approaches the same value as x approaching a from the left and from the right. And again, the limit of g of x as x is approaching a also exists. It means that actually g of x is approaching a certain value when x is approaching a, and it's approaching the same value and x is approaching a from the right. The first rule that we have here, we can see that actually we'll give an example later on. For now, I just want us to go through these rules. It means actually, if you have the limit of x approaching a, if you're evaluating the limit of x approaching a of f of x plus g of x, you'll get the same answer as it's just evaluating the limit of x approaching a for f of x and evaluating the limit of x approaching a of g of x. So basically, this is called a sum rule of limit laws. And same thing for difference, or it means actually evaluating the difference between f of x minus g of x. It is the same thing as just evaluating f of x alone, minusing the evaluation of g of x alone. The third law is just say that actually, since a constant is just the number, so basically x approaching a, it does not affect that constant. So basically, evaluating the limit x approaching of c times f of x. I know that right now these things, they seem general, but we'll give an example on what do we mean. Then the limit, we can might as well just take that constant out, that again get to multiply that constant with the limit of x approaching a of f of x. And same thing with the product. The limit of the product of f times g is the same thing as the limit of f of x times the limit of g. Lastly, the limit of f of x over g of x is the same thing as the limit of x approaching of f of x all over the limit of x approaching of g of x. But this can only happen if the limit of g of x approaching of g of x is not equal to 0, because otherwise you're going to have 0 in the denominator. Sorry. And that is undefined. So basically, these are what we just explained here in words. So I'm just going to skip this. If you need to read, you'll read on your own, because I remember we're sharing these notes. But otherwise, if you look at the sum law, here the sum law, meaning talking about the first one, if f of x was approaching, we said it exists. So let's say f of x approaches L and g of x is approaching M. It means actually the limit of f of x approaching a of f of x plus g of x, that answer should also approach L plus M. Remember, it means that actually this will have to be equals to L and this will have to equals to M. So it means actually the answer of evaluating f of x plus g of x, the answer should just be L plus M. Let's look at this example here to use the limit laws that we evaluated earlier. Let's look at the first one. Remember, here we're told that the pink function is f and the blue function is g. So Roman figure number A is asking us to see, look at x approaching -2. -2 is here. -2 is here. So we evaluate f of x plus g of x. So looking at f, remember that law said actually evaluating the sum, you can evaluate them individually. So when you look at f, f is approaching 1. I believe you can see from here, both from the left and from the right, the function is approaching 1. The y value is approaching 1. So we can say that 1. And again, we have a constant function here, constant rule here. It says that actually the limit of a constant times a function is the same thing as a constant times a function. So basically, it means that from here we can have plus 5 into, so looking at g is this function here, so approaching -2, both from the left and from the right, it goes to -1. So from here, we're going to have 1 plus 5 times -1 is -5. So 1 minus 5 is -4. I hope that part was a bit easier. Let's look at number B. Number B, we said we're going to look at x approaching 1. Here's 1. So so remember the product law said the limit of the product of function is the same thing as the product of the limits of the functions. So basically, when you look at f of x, f here it is, so approaching 1, the function is approaching 2. And when you look at g of x, coming from the left, it goes to -2. Coming from the right, it goes to 1. So for that, it means the limit does not exist. So because one of the function, the limit does not exist, it means actually for the whole question, it means actually the limit of x approaching 1 of f times g, we say that the limit does not exist. I hope that one is clear. Let's look at number C. Number C, we're talking about x approaching 2. 2 is here. So we said we want to evaluate x approaching 2. So remember that last law, the quotient rule, it said the limit of f of x over g of x is the same thing as limit of f of x all over the limit of g of x. So looking at f is this function here. So we could say that it approaches 1.5, 1.4, somewhere there. So we can say that the limit as x approaches 2 of f of x, we can say that it's 1.4. Let's say for argument's sake. Then for g of x, looking at g from the left and from the right, the function is approaching 0. So it means actually we're going to have 0 in the denominator. So in that case, because we cannot have 0 in the denominator, we say that the limit does not make sense, or the limit does not exist. Basically, this is just evaluating what we've been talking about. We did get this -4. We evaluated number B. We said the limit does not exist. We said the limit does not exist because the left-hand limit and the right-hand limit are not the same. And lastly, number C, we said because the limit of as x approaches to g of x is 0, we say that the denominator we get 0. So for that, we say that the limit does not exist. I hope that was a bit clear. Remember, we'll be sharing the notes. If you still want to go through that part a bit slower, you'll get the slides and you go through it. So these parts are just explaining what we went through. So looking at number B, remember, is the one that we're talking about. Let me go to number B. This is number B. We said the limit does not exist because approaching 1 from the left and from the right are not the same. So for you to be able to evaluate this, instead of saying that the limit exists, it's rather, you may rather just want to look at one-sided limits and not look at x approaching 1. Rather just separate the two and evaluate the limit approaching 1 from the left and evaluating the limit approaching 1 from the right. So in that case, you'll be able to evaluate this function. But if you just want to say the limit approaching 1, remember we want the limits to be the same. So in that case, because now you want them to be the same, they will not be the same. But otherwise, evaluating them individually, coming from the left and coming from the right, you'll be able to get the answers. And okay, so now we want to, from the, if you look at this law, let me go back to these laws that we had earlier. If you look at these laws, and especially number 4, right? If you look at number 4, suppose g of x is the same thing as f of x. So basically it will mean that basically here we have f of x. It means that we'll have f of x squared. So basically means that we'll be evaluating the limit as x approaches a of f of x all squared, and it means that even from the right hand side, it means actually, remember that it means that you're having f of x here. So it means it will be the same thing as the limit x, sorry for my bad handwriting, the limit of f of x all squared. So basically evaluating the limit, meaning the product of the limit is the same thing as the limit, I think the product of the limits. So the limits of the product is the same thing as the product of the limits. I hope that makes sense. So basically from here, we can say that actually we can generalize and make this 2 to be n. So it means actually limit of f of x to the power n is the same thing as the limit of f of x all to the power n. And that is what we are coming to when you look at the notes that we have here. So for that, we develop this rule number 6, saying that the limit as x approaches a of f of x to the power n is the same thing as just evaluating that f of x, then that answer just the ratio to the power n. It says where n is positive. I hope you understand why n needs to be positive. Remember that remember that n is an exponent. If it's negative, it means it goes to the negative, right? It goes to the denominator. And if it goes to the denominator, it means actually there is a chance of the limit not existing, especially if the limit of f of x, especially if this limit was going to 0. So it might not exist. So basically for us to be able to, so that the limit exists, we need n to be a positive integer. So to be able to prove this, because remember we're doing maths, so for you to be able to prove this, there is a proof that is called induction. So I'm not going to get into this because it's a whole different new topic of proving by induction. So I'm going to leave that. If you want to know what is proving by induction, that will benefit you. That will benefit you very much mostly. So you can go and look at proving by induction, or actually what does prove by induction means. In addition to these laws, suppose C is a constant, meaning our f of x is a constant. So the limit of a constant, it is still a constant, which makes sense because remember, it means that actually we want to see how y behaves when x is approaching a. So y is equals to c, y is equals to c. This is just a constant function. So c will be here. So even if a is here, so x approaching a from the left and from the right, y will just be constant. So it does not matter. So meaning this will be our x-axis. So if a is here, we're coming from the left or coming from the right, the function does not approach some certain value. It's just, it just doesn't matter. So the function will always be c, whether x is here, x is approaching a, or x is approaching b, or x is approaching some value here, the function will just continue just being a constant function. So it does not depend on, so this y does not depend on x. And when you look at this function here, sorry, the rule number 8 here, it says that actually the limit of x approaching a of x is equals to a. Remember that this is our y. So basically means this function, we're talking about y is equals to x. So y is equals to x. And remember that y is equals to x is a straight line function. So it's a function that goes something like that. So this is y is equals to x. So if a is somewhere here, right? So x is approaching, remember that y is equals to x. So if x is approaching a, it means actually the corresponding y, it has to be the same and it has to be a as well. So number 8, that's why number 8 makes sense. Because the limit of x approaching a of x, the x, your answer would be a. I hope that makes sense. Number 9 just builds on number 8. So it means here, if we have x to the power n, could be, if n is 2, that means you have a parabola. X approaching a of that parabola of x squared, it will just be a squared. This was this rule mean. And again, n needs to be a positive integer. And for the very same reason, I want you to take a moment and or investigate, why do we need a positive integer? Why do we need to specify that n needs to be a positive integer? If n is negative, what happens? Or which situation will not work if n is negative? I hope that part is clear. So basically, for me, I just want to state this rule. There are proofs to these rules, but I don't want to get into that. Remember, we said we just want to go on the surface. We have another rule here, the one that talks about the radicals. It says actually the limit of x approaching a of root n of x is the same thing. Just remember, from number 8, from rule 8, we said the limit of x approaching a of x is a. So this rule number 10, it builds on top of that. Remember, we said the limit x approaching a of a, x approaching a of x will just be a. So it generalizes, means that actually, even if you have the nth root of x, evaluating that limit, you'll just still get the nth root of a, because the limit of x approaching a of x is a. And again, n is a positive integer. Why? Think about the think about square roots. Okay. Just think about, why does n needs to be a positive? And again, more interestingly, says if n is even, assume that a is positive. Remember that a is inside the square root, so a needs to be positive. So if, for example, inside the square root, you cannot have a -4. In real numbers, that is unknown or that is undefined. But otherwise, you can have the cubic root, because n is odd, you can have the cubic root of -27. Right? Because if the root is odd, then the number inside the root can be in positive or negative. But if it's even, then the number inside the square root definitely needs to be positive. Maybe to answer you, the reason why you cannot have square root of -4 is because there is no number. Remember that there's a number 2 here. So there is no number such that when you raise it to the power 2 or that number squared, you can get -4. All the numbers, when you square them, the number has to be positive. That's why for square roots or for even number roots, you cannot have a negative inside the root. So basically, in here, the reason why we can have that, your answer is going to be -3. Reason because -3 cubed, -3 squared, you get 9 times -3 again, -27. So for odd roots, that's why you can have negative numbers inside the roots. And to generalize it here, we're just talking about x. So we're generalizing, just say that f of x. So basically we say that the limit of x approaching a of the nth root of f of x is the same thing as the nth root of the limit of that f of x. And again, if n is even, we need the limit here to be positive, because inside the root, we cannot have a negative number. I hope that part is clear. Here, we're talking, say that in section 2.5, which we'll do after the following session, I think that will be next week, Monday. It can be used to prove this root, this 10, again, this law number 10. But otherwise, I will not go into that. But otherwise, for you to be able to do this, to prove this number 10, we need to have done that section, because it explains in detail what you need to know to prove that rule. Let's take for an example. So now we want to evaluate. We have some function here, 2x squared minus 3x plus 4. So we want to evaluate this function when x approaches 5. And we want to use these limit laws that we just learned. And again, for number B, we say we want to evaluate x approaching -2 of this rational function. I hope you did Google or you did go and look at what is a rational function. And again, we said rational functions is when you have a polynomial in the numerator and another polynomial in the denominator. And I hope that you did Google what is a polynomial. Let's look at number A. So we have a quadratic function there. We have a parabola there. So we want to evaluate. So according to that, I remember that first law, the one that I was talking about, the summation of function. Maybe let me just run quickly to those rules. Yes. So basically, let me just look at these rules. We did say that the limit of f of x plus g of x is same thing as the limiting of f of x times g of x. We said same thing for the difference, and for the constant, we said we can take the constant out. Number four, we said multiplying two functions and evaluating the limits is the same thing as just limiting the functions individually and just multiplying the answers. And we go to generalize that by this rule here. We said if g of x was same thing as f of x, then we got that. So let's see if you can use those rules. Let's see if you can use those rules to evaluate our example. So here we said we want to eliminate or evaluate the limit as x approaches 5 of this function. So we can use the summation and the difference rule or subtraction rule and just separate all these, or we can separate all these points, or I mean, sorry, all these, what is the word? Yeah, that we can take all these individually and you get to evaluate them individually. So, and again, here we can use that rule of constant. So basically, you can take the constant out and get to evaluate the limit of x approaches 5 of x squared. Same thing here, 3x, we can take the constant out. And here we just evaluating the constant. So remember we said the limit of x approaching a of c should still give you a c. We spoke about the constant function. So we expect here our answers to still be 4. And here, remember we said the limit as x approaches a of x, it will just be give you a. I gave you an example by talking about straight line function y is equals to x, and we get 5. So 3 times 5 is 15. And here, remember that here you have x squared. X squared is the same thing as x times x. So basically what we did here, we can do it here by just evaluating limit of x as x approaches 5 times the limit of x approaches 5. So basically for both of them, they go to 5. So you end up having 5 squared. So, and simply you get your answer, and you can go to number B. Remember, number B uses the quotient law. The quotient law said the limit of x approaches a of f of x over g of x is the same thing as the limit of x approaching a of f of x all over the limit of x approaches a of g of x in the denominator. So evaluating f of x, so we can say that this is our f and this is our g. So basically eliminating this quotient. So basically we can just take the numerator evaluated individually, the denominator evaluated individually. Remember we said we can only use this law if the limit of the denominator is not 0. If the limit of the denominator is 0, then using that law is wrong. So can start first evaluating the denominator, evaluate the denominator. We can do what we did with number A, just get to look at all these individually, all these factors individually. So basically we can do that even for the denominator. Then from there we get to see that actually for a cubic function, when x approaches -2, it goes to -2 cubed. Squared for a squared function, it goes to -2 squared. For a constant, it just goes to that constant. Here this constant is still goes to 5, and 3 times the limit of x approaches -2 of x, you still get -2. So evaluating this or just calculating, we get -1/11. So as you can see, these two examples that we just did, we did not use a calculator, but we are able to come up with an answer. I know this was the easy one, but there's some examples that we prepared here, even just to revisit the examples from the previous lecture so that we can evaluate these limits. Now, if you look at number A, we said our function is 2x squared minus 3x plus 4. So basically, if you look at the answer that we got, remember that the answer that we got, the limit as x approaches 5, we got 39. But now, if you get to notice the very same function, if you had to substitute 5, we get the same number that we got when evaluating the limit. And the reason for this, or in other ways, we could have just got the answer by just doing a direct substitution, or just substituting 5 where we see x. And the reason why this is true, or we can be able to do the same thing for number B. Number B, remember, we had a rational function, and we ended up getting -1 over 11. So basically, if you take number B and do a direct substitution, you'll get the same answer. And the reason for this is because direct substitution always works for polynomials. So again, if you're lazy to go look for what is a polynomial, this is the time you can see that this word polynomial keeps on coming. In case maybe you can't, you still don't understand, polynomial is any function that follows, let's say this is I maybe say starts from 1 until n of some ai x to the power I. So basically, this means if I remember, this is summation. Summation, it means addition. So meaning if I is 1, it means that we're going to get a1 x to the power 1. If x I maybe n, let's say n ends with 3, so we're going to have ax. So this should be I minus 1. So basically, this will mean it will be 1 minus 1, which is 0. Then when I is 2, we're going to get I2 x to the power 1, because that is 2 minus 1, plus a3. Then this is going to be ax squared, because remember 3 minus 1 is 2. So basically, if we let n to be 2 here, so any function that follows this kind of rule, we say that it's a polynomial. I'm sorry for the very bad handwriting, but otherwise, such function that follow this rule, n can be any number, can be any integer. So it means that actually when n is 3, it means that here we said when n is 3, then if we turn n to be 4, it means your highest power will be 3, and that's a cubic. So for this one, it means that we have a quadratic here. So that is the definition of a polynomial. A rational function is when you have a polynomial over a polynomial. So such function, they always have, you can always use direct substitution to evaluate their limits. And to generalize it, to say direct substitution property, we say that if f is a polynomial or a rational function and a is in the domain, it's very, very important, especially for rational function, because if the function is not defined at that point, it means that point is not part of the domain. So if that point is a part of the domain, then the limit of that rational function or of that polynomial as x approaches a, your answer is just as good as just doing a direct substitution, meaning substituting x for a, which gives you f of a. So these kind of function that where we can use direct substitution, in other words, the polynomials and the rational function, such function we say they are continuous. They are continuous at a. And that is a very big term in mathematics to talk about continuity, or to talk saying that a function is continuous at a point. And we'll talk about that on Monday in detail and get to explain what do we mean a function is continuous, which function is not continuous. Let's look at the next example. So basically here we have x squared minus 1 all over x minus 1. So here, please note that we have a rational function here, x squared minus 1 over x minus 1. But though this is a rational function, we cannot use the direct substitution property, because 1 is not part of the domain. Because if you substitute 1 here, you're going to have over 0, and over 0 is undefined. So we cannot use a direct substitution here. It will fail. So for us to be able to do that, and again, we cannot use the quotient law, because on the denominator, we're going to have a denominator of 0. So we need to find a way to simplify the function. But if you look at the numerator, we have x squared minus 1, which is the difference of 2 squares. So we can factorize that and get x minus 1 times x plus 1 all over x minus 1. So in this case, you can see that, remember we said the limit is approaching 1. It is not equals to 1. It approaches 1. So we just want to see what happens around 1. So it's not 1, and because x is not equals to 1, then from there, we can cancel the denominator with x minus 1. So basically, x minus 1 cancels, and you're just left with x plus 1. And in that case, you just have a polynomial, and you can do a direct substitution, and voila, you got an answer. So hope you can see actually from the previous example, from the previous lesson, we had such function and it did go to 2, but we had to use a calculator for it. We have another example here. So I hope you can see that we cannot use a direct substitution, because if we substitute h here, we're going to have 0 in the denominator. So we cannot evaluate him by using the direct substitution. So the choice that we have is to try to simplify the function itself. So what we can do, we can let f of h be this function that we're trying to evaluate. Then from here we have brackets. We can multiply out the bracket. When multiplying out the bracket, we get 3 squared, which is 9, then 6h plus s squared minus 9. So obviously the 9 cancel out. Sorry. So obviously the 9 cancel out. You left with 6h plus h. You can factorize h. And from there, the h can cancel, and you're left with 6 plus h. And once you left with 6 plus h, now you have a polynomial that you can just simply do a direct substitution and get an answer of 6. I hope that was clear. Okay, we have another example here. If you'd like, you can pause and try this first to try to evaluate, because as you can see, and again, this example was there in the previous lesson. So you cannot substitute 0 right away. So you have to find a way to manipulate or to simplify the function. So in this case, because of a root, you cannot say that you break down the root or anything. So basically, you can multiply out, but rather what we can do, and please know that we said 0, we cannot do a direct substitution. And again, you cannot apply the quotient law immediately. So we can only simplify this by rationalizing the numerator. Rationalizing the numerator is using what we know is the difference of 2 squares, and using that to get rid of the square root in the numerator. That's what we mean by rationalizing the numerator. It means we want the numerator to be rational, meaning we don't want it to be radical. So what do you do? We can multiply with this, what we have in the numerator, but instead of minus here, we have a plus. Please note that this minus is not inside the square root. It's outside the square root. So that's what we mean by rationalizing the numerator. So we can multiply both. And as you can see from here, we're going to have difference of two squares by multiplying this out because they are the same except for the sign that divides the terms. So as expected on the numerator, on the denominator, there's nothing we can do. We can multiply t squared with the square root, so we're just going to leave it like that. From here on the numerator, mind you that after multiplying all these, you're going to end up with the square root of t squared plus 9, right? All squared, the first term squared minus the second term, which is 3 squared. Oh, my handwriting is very bad. Let me see if I can get another handwriting or another something that I can use. So basically going to have the square root of t squared plus 9, right? Remember, this is our first term. We can put it in brackets. All squared minus 3 squared. So obviously from here, the squared cancels the square root. That's why we left with just t squared plus 9. Then 3 squared is 9. Please note that this comes from knowing that x squared, minus y squared. When you factorize this, you just get x minus y into x plus y. So all these things that we're doing, it comes from here, from what we know about the difference of two squares. Let me just erase this so that we can continue. So all this process that we just been doing, it's called rationalizing the numerator. Even if the root was in the denominator, it would now, in that case, it will be called rationalizing the denominator. So after simplifying here on the numerator, we're left with t squared plus 9. So as you can see from here, the 9 will cancel the 9 and we just be left with t squared. So in other words, this t squared, because it's been factorized, we can take t squared, cancel in the t squared. So on the numerator, we just left with 1 because this t squared, it canceled with another t squared. So we just left with t squared plus 9, the root of t squared plus 9, then all that plus 3. So from in this case, we can evaluate or we can do a direct substitution, substitute t to be 0. You're going to have 0 squared, which is 0. 0 plus 9 is 9. Square root of 9 is 3. 3 plus 3 is 6. So ultimately, your answer is 1/6. And I hope you remember this because on the previous lesson, we ended up getting 0.1666 using a table. So basically now we evaluated the very same limit, but without using a calculator. So far we've been talking about, earlier we spoke about the two-sided limits. Remember we said the limit exists if the limit from the left and the limit from the right are the same. I hope you remember that. We said this is the case, the limit of x approaches a of f of x is equals to L, if and only if the limit, the left-handed limit is L and the right-hand limit is L as well. So basically these one-sided limits, we can use limit laws as well. So the limit laws that we just did, they're not only limited to two-sided limits, but even if you take one-sided limits, the limit laws still applies. Let's take for an example. Remember an absolute value. If you don't know absolute value, please go and check absolute values because this is one of the very important concepts in calculus or in first-year mathematics. For those who don't know, an absolute value is a function that that makes sure that actually its output is positive. Its input can also be negative or positive, but it makes sure that its output is positive. So basically, if the function y is equals to let me say y is equals to absolute value of x, it means If x is positive, then leave x to be positive like that so that we have positive values. But if x is negative, multiply that negative number with a negative. So in other words, if you look at these two functions here, meaning we end up having y is equals to x when x is positive, right? And here we have y is equals to negative x when x is negative. Maybe let me help you draw that. Remember that x is positive is this side. So this is our x-axis. We have our origin there, and this is the y value, right? So y is equals to x is a function that goes like that. And he said this can only go when x is positive, meaning on this quadrant. On the first and the fourth quadrant, x is positive. So we have y equals to x, which is a straight line going like that. But when x is negative, meaning x is negative for the second and the third quadrant, meaning on the side, we use the y equals to minus x, meaning it's a line that goes like that. So basically, if you look at this, y does not go on the negative side, or y doesn't get to be negative. Our y is always positive. First and second quadrant, y is positive. So all we're trying to do is to make sure that the output, remember here, our x is negative, but the output, because x is the independent variable, y is the dependent variable, y depends on x. So our output, even though you've inputted the negative x, our output is positive. So we make sure that in both cases, our y is positive. So that's what that's why we have absolute values, or that's the reason, or that's what absolute values means. In other words, I believe you know that distance cannot be negative, right? Distance cannot be negative. Yes, velocity and all displacement and all those others, they can be negative, but distance cannot be negative. So because we want distance to be a positive number, whether you're going from point A to point B or from point B to point A, the distance have to be positive. That's where the absolute value guy comes in, to make sure that whatever distance that you've traveled, even though you're going from A to B or from B to A, the distance is always positive. Yeah, so basically from the function that we just drew, remember we said absolute value function, it looks something like that. So basically coming from the right, it means coming from the side which using the values that are bigger than zero. Using the values that are bigger than zero, it approaches zero as well. And again, using the values that are less than zero or coming from the left, we still go to zero again. If we still approaching zero coming from the left, we still approaching zero. So meaning the limit from the left and the limit from the right, both of them are zero, right? And remember we said when the limit from the left and the limit from the right are the same, we say the limit exists, and that limit, it will be zero. So basically the limit as x approaches zero of the absolute value of x, we say that it's zero. I hope that was clear. We have another example here. If you'd like, you could try the example and see if you get the example, but this example says that actually we should prove that the limit does not exist. So let's start first with the absolute value. We already said the absolute value is positive when x is positive. Remember that x in the denominator does not change. The one that is changing is the one in the in the numerator. So the absolute value we said is positive if the inside the absolute value sign is positive. So if x is positive, and is negative x if the inside of the x is negative. Right? So if you look at this is equals to 1 because we have x over x, and we have minus x over x, which is equals to minus 1. So you have a function here, if maybe you call this y, right? And you want to draw this kind of function. We are saying that when x is positive, remember that x is positive, this side, the function is equals to 1. So if maybe y is equals to somewhere here, so it means it's going to be a function that just goes straight like that. When x is negative, which is this side, y is negative. So if negative 1 is somewhere here, the function will get to look something like that. So when x is positive, we just have a constant function, and y is negative, we still have another constant function. So now, from this function, it means actually approaching 0, coming from the right, from the side that are greater than 0, we go to 1. And coming from the left, we are approaching 0. So we're approaching, y is approaching -1. X is approaching 0 from the left, y is approaching -1. So we're approaching, as x goes to 0, our limit from the left and our limit from the right are not the same. So since all that they are not the same, we say that the limit does not exist. I hope that was a bit clear. So there's the answer. And please know that these are inequalities, they do not have equals to. They are strictly greater than and strictly less than. So that's why you see this graph having these open dots here. We have another example here. So we have, this is called the root function. So if x is greater than 4, we have this root function. And if x is less than 4, we have a straight line. So now we have to determine whether x approaching 4 exists. Meaning if the limit from the right and the limit from the left are the same. So looking at this function, we said the root function of x minus 4, we said we use this function if x is greater than 4. So meaning if you look at the values that are greater than 4, 5, 4.5, 4.2, 4.1, all those values that are greater than 4, and we evaluate the limit. So those values are greater than 4, or we have, remember we said the root, the limit of a root is the same thing as the root of the limit. I think that was rule 8 or something like that. But we did evaluate that, saying that actually limit of a root is the same thing as the root of the limit. So meaning we can take the limit inside the function and we have a straight line, which is a polynomial. So we can use the direct substitution. So coming from the right, we get our limit to be 0. And now coming from the left, meaning the values that are less than 0, the function here, this piecewise function is telling us that we have to use the straight line, 8 minus 2x. So approaching, which is a polynomial, which is a straight line. So basically approaching 4 from the left, we can do a direct substitution. 2 times 4, it's 8. 8 minus 8 is 0. So for the fact that we are coming from the right and coming from the left, we get the same value. It means actually the limit exists and that limit is equals to 0. I hope that is clear, and that I hope that actually so far you guys have grasped on this. You have grasped on this limit laws, and basically this function that we've been, this piecewise function, this is how the function gets to look like. Less than 4, a straight line. After 4 is a root function, and this is how the root function gets to look like. We have another example here called the greatest integer function. Greatest integer function. So basically, this notation, it means the largest integer. So basically what it means, let's take a number line. Let's maybe say 0. Remember the integers are the whole numbers. So let's say you have -1 here, -2, -3. Let's say here you have 1, you have 2, you have 3, and so on and so on. Let's take, for example, this -12. -12, it's somewhere here. Right? Remember these values, they keep on increasing. So basically 3 is greater than 2, 2 is greater than 1, 1 is greater than 0, 0 is greater than -1. So basically this -1, half, -half, the number that is the greatest integer, or the number that is bigger than it, the highest integer that is bigger than it will be -1. I hope that is clear. Root 2 is somewhere here. It should be 1 point something. I forgot what is it. But otherwise, the biggest number that it's bigger than, it's 1. So that's why the largest integer of root 2 is equals to 1. Pi is 3.14 something something. The biggest number it's bigger than is 3.14. It's somewhere here. So the biggest integer would be 3. 4.8, the biggest number, it's 4, not 5. It's approaching 5, but it's not bigger than 5. But the biggest integer that it is, it's not the same thing as rounding up or rounding down. We're just looking at, we just want our values to go to whole numbers. So basically we wanted to just to go to the biggest whole number there is. So basically it's asking us to find the limit of this to show that actually this function does not exist. By the way, if you draw this function, it gets to look step by step like this. It means that anything that is between 0 and 1, including 1, all those numbers, it will be, sorry, -1. All the numbers between 1 and 2, they'll become 1, meaning 1.9, 1.8, 1.5, the answer is 1. So that's why the function gets to look like it's steps like this. So basically, it means actually this function, if you look at the absolute value, being 3, meaning we're talking about here, we're talking about this function here, this one here. So we're talking about between 3 and 4. So, so meaning for all the integers that will result, all the greatest integers that will result in 3 are all the numbers between 3 and 4, including 3. So meaning coming from the right, meaning the numbers that are bigger than 3, will go to 3, but coming from the left of 3, it means you're talking 2.9. And now those 2.9, though they are bigger than 2, they'll go to 2, and that 2 is not equal to 3. So basically, that's why the limit from the left and the limit from the right are not the same. Sorry, this is supposed to be, this is a typing error. This is supposed to be a 2. So meaning the greatest integers that will result in being 2 are all the values between 2 and 3, including 2 itself. That's why the inequality is an equal sign here. So that's why the required limit does not exist. I hope that one was clear. Let us go to the last part of our lesson. Suppose you have two functions, f of x and g of x. Both of them are defined when x is near a. Remember we said we don't care at a, but f of x being less than g of x, let me just draw. If maybe f of x is a function that looks like this, g of x will be another function. Maybe, let me see if I can use the other pen. So suppose you have some function, let me call that our f, and another function here called g. So f of x, no, actually I mix the function around. So suppose actually you have your f of x and you have your g of x. So basically it means this f of x being less than g of x, it means actually g is above f of x. So it means actually g of x is above f of x. That's what this notation, that's what it means. So basically, okay. 2 minutes. So basically, that's what it means, meaning the function of f is always lower than the function of g. So it means actually the limits of f will always be lower than the limits of g. And again, so now we get to the most important theorem in our class here called the squeeze theorem. So suppose you have some three functions, some f of x, g of x, and h of x. And all these functions, they are defined when x is near a, not specifically at a, just near a. This means actually, in other words, your f will be, Your H will be there, your G will be somewhere here, and your F will be somewhere here, meaning the function of G, let me say this one is G, this one is H, and this one is F. So meaning the function of F is always between the function of H and the function of, between the function of H and the function of F. So basically you're saying that if this is the case and the limit of F, the function, this lower bound or the function that is below, if its limit and the limit of the function that is above H goes to L, then definitely because G is between F and H, it has to go to L as well. That's what we just mean. And squeeze theorem for other textbook, they call it the sandwich. Other textbook, they call it the pinch theorem. So all this theorem, we are saying that if G is between H and F, then, and both F and H, they approach L as X is approaching A, then definitely G has to approach L as well. Maybe let's take an example. So now we want to evaluate the limit X approaching 0 of X squared sine 1 over X. We want to prove that actually it approaches 0. So we don't know how this function of sine of X squared sine 1 over X, we don't know how it looks like. But for us to be able to evaluate this function, we want to use the squeeze theorem. Even if we try to use the distributive law or that product law of saying that evaluate X squared aside, evaluate the sine aside, but we all know that actually X approaching 0, sine 1 over 0 is not defined. It does not exist. So we need to come up, we need to use rather, we use squeeze theorem. So meaning basically we need to find some function f of x or some function h of x such that this G is in between these functions and these two functions, because remember we are asked to show that this limit goes to 0. It means that these limits, the limit needs to be 0 as well. I hope that part is clear. So obviously the h of x needs to be bigger than G and f of x needs to be lower than f of x. And both these two functions need to approach 0. Please don't stress, it's actually easy. We all know that the function of psi generally is between -1 and 1. Or you can just say that the function of sine theta, the function of sine theta, we know that is between -1 and 1. So same thing as the function of 1 over x, it will still be between -1 and 1. So if you look at this here, remember with inequalities, if you multiply with a positive number, the inequality sign does not change. It only changes if you multiply with the negative number. But from what we have here, if we multiply by x squared, remember x squared is a positive number. So it means the inequality sign does not change. So meaning we can multiply by x squared throughout, and x squared, meaning here, the x squared, this is a parabola that is of a smiley face, minus x squared is a parabola of a sad face. So basically it means the function of x squared times sine 1 over x, it will be a function that is in between these two functions. I hope that part is clear. So now we can evaluate the limit of x approaching 0. It's a polynomial. We can use a direct substitution to get 0. Same thing for x squared. We can use the direct substitution. The limit of x squared also goes to 0. So we see that actually now our limit of x approaches 0 of x squared times sine 1 over x is between 0. So from that, by squeeze theorem, it means that actually the limit of this function, x squared times sine 1 over x as x approaches 0 is equals to 0. So that's how we get to use squeeze theorem. The function on its own, it's hard to evaluate. So for you to be able to evaluate, you find other functions that you can compare with this function, one function that is bigger than it, another function that is smaller than it, such that these two functions that you just chose, they go to the same limit. Then definitely this middle function will also go to the same limit. I want to stop here. for today. So that's it about the limit laws. In our next class, we'll get to talk about the absolute delta definition. So basically, that is the part that sums up these parts of limits. Because in the previous lesson, we spoke about approaching. We said X is approaching some certain value. We said when X is getting closer to A, but that is ambiguous. When you say X is approaching A, what do you mean? How close is close? I almost said something, but let me keep quiet. But when you say X is approaching, X getting closer to A, that is still ambiguous. It is not mathematical somehow to say such, because even distance, somebody can say that 1 kilometer is a very long distance, but someone can say that, but there's still 400 kilometers. It is not far, it is close. Compared going from Cairo to Cape Town, that is far, but just driving from Joburg to Durban, that is not far. So something being far and being close, that is a relative. And for us to say X is approaching, X getting closer, nah, it's not so much mathematical. So basically, on the next lesson, we'll be getting deeper into that and explaining exactly what do we mean when you say we are getting close. And such lesson is called the absolute delta definition. And again, that is very much important. Please pay attention, concentrate, because you will come across that when you get to do your third year mathematics. And for now, today, that will be all for today, and we can stop here. Enjoy your evening or enjoy your day.